Good morning, my name is Maxine Major with the Naval Information Warfare Center Pacific. Today I will be presenting our paper, Informing Autonomous Cyber Deception Systems with Cyber Expert Performance Data. This paper discusses how lessons learned from a real-world human subjects experiment can help inform autonomous cyber deception by leveraging data typically available only to a cyber defender. And these are the topics that we'll be covering today. Deception is as old as warfare, and in cyber warfare this is no different. Cyber deception is a rapidly advancing field which aims to offset the difficulties of cyber defense by casting doubt and misleading attackers. This is more than just honeypots. Anything on a defender's domain can be faked, which includes network devices, user accounts, vulnerabilities, etc. Cyber deception can serve as an early warning that an attacker may be present. Deception can disrupt attacks at any stage. And any interaction with deception is a waste of time and resources, provided that investigating the deception does not help the attacker discover later deception or real assets. Any belief in the validity of deception corrupts attacker knowledge, and interactions with deception waste time. A major advantage to using cyber deception is that it levels the playing field. Instead of the attacker only learning the truth about a network, with deception, the attackers can no longer trust their tools, their results, their knowledge deteriorates, and even what they perceive to be successes and failures they may doubt. Because any interaction with deception is known to be malicious, this cuts through the noise and false positives, increasing the effectiveness of defenders, and allows defenders to learn about the adversary through their interactions with the deception. Deception does have a limitation, however, of just being one more thing that defenders have to maintain. However, automating the deployment and configurations of cyber deception reduces this overhead, as we'll discuss later. So, autonomous cyber deception takes this idea a step further. First, it reduces the defender's overhead with less placement and configuration decisions to make. An autonomous solution can learn from the attackers in real time and adapt in real time based on inputs and prior history of activity. If deception is dynamic and learns based on attacker actions, then it is less likely that an attacker will learn how to defeat the deception. There will be some pitfalls along the way, however. Human-machine teaming can cause over-reliance on the technology, as evidenced by self-driving cars. And because cyber warfare is an arms race, counter-deception techniques will naturally follow. The Tularosa study is a human subjects experiment that measured the effectiveness of deception against attackers. Up to 139 subjects took part in a 2-day hacking exercise, and they were split into one of 4 conditions, through which they were either on a network where deception was present or was not present, and they were either informed or not informed that deception might be present on the network. The decoys mimicked generic workstations and servers similar to real targets on the network. They were low interaction decoys, which could be scanned, but no real services existed to exploit. Attacking the decoys resulted in no value that helped participants identify or attack any of the real targets. Multiple results from the Tularosa study indicate that the presence of deception or being informed of deception reduced the impact of many cyber attacks measured. The combination of deception present and being informed of deception was the most impactful. And this is important because the use of deception does not need to be secret to be impactful. So for a defender, vast amounts of data could support monitoring and measuring the effectiveness of deception. But here we mention a very simple set of features that a deceptive defender could monitor while deploying and then evaluating the efficacy of cyber deception. This list includes network data that is already available to a defender and additional data collected from a deception capability. Similar features were used in the Tularosa study to measure the impact of deception's effectiveness. These include network traffic to decoys, use of admin accounts, and lower numbers of IDS alerts which were correlated with less success overall during the experiment. These are the types of features that can be monitored in real time, and the values associated with these features will change as an attacker interacts with the service or as the deception configuration changes. By tracking an attacker's activity in relation to these features, we can then learn their intent, even if we can't directly observe their specific tools or strategies. Where an attacker's action over a feature can be observed, that action can be categorized roughly in terms of what phase of attack is being executed. The list shown here is a high-level, simplified classification for our model, but other more robust attacker action classifications exist. These include the cyber kill chain, popularized by Lockheed Martin, which describes a similar 7-phase approach to an attack, and the MITRE attack framework, which classifies tactics and techniques at a much more granular level. Patterns of these TTPs can be tied directly to known threat actors. And the attack framework is also used to support automated pen testing tools such as MITRE's Caldera and Atomic Red Team. Our space of attacker actions roughly correspond to the cyber kill chain model as shown here. We provide examples of how these data categories line up with data collected from the Tularosa study. Activities that are classified as belonging to one of these stages can provide insight to how much of a foothold or presence the attacker has on the network. And the most interesting thing about this is that deception can play a huge role in triggering and mitigating each of these types of alerts. The defender's goals differ from those of the attacker, and we categorize those goals in terms of defensive and deceptive. Because our focus is on deception, we simplify defensive techniques into very high-level categories. Monitor IDS, or network, monitor HBSS, or the hosts, and do nothing, or wait. If the IDS catches an attacker, then we didn't need deception to detect that specific activity, but we may launch a new deception in response. So information from non-deception tools can still support the deployment and configuration of deception. Even though we don't go into detail on purely defensive abilities, if we need more level of granularity, sources such as the OpenC2 language specification can provide that detail, and the Tularosa study also has several examples where purely defensive tools can show deception-impacted patterns of activity, such as the domain accounts and IDS alerts. Similar to defensive actions, deception actions are oppositional to the attacker's goals. These include delaying attacks, deterring attackers, and polluting attacker knowledge. We provide a list of technically feasible deception actions that include placing decoys, network traffic deception including a ping responder, false success responses, and options to speed up, slow down, and drop connections on the network. Other deception is based on false user accounts or credentials for which any use is indicative of malicious activity, and the context for that use can reveal the attacker's level of access or intent. The Tularosa study showed that even with only static non-responsive decoys, the deception was effective. It is our assumption that even more nuanced deception, particularly one that adapts alongside the attacker, will be even more effective. One thing that is not present in the list of deception actions here is the psychological deception that was present in the Tularosa scenario. The condition in which participants were informed that deception might be on the network, even though no deception was present, this showed some impact towards supporting these deception goals. However, even technical-only deception can still result in psychological effects such as confusion and frustration, as demonstrated in our prior work. Defensive deception actions also directly mitigate the attacker actions depicted prior. For every type of attacker action, at least one deceptive action has the potential to disrupt some component of attacker activity at any given stage of the attack. With deception that learns from adversarial actions over time, we can start to piece together a profile for an attacker that can then be used for targeted deception. We can learn what types of targets are of interest and spin decoy services or files to match. We can learn how interested they are or how stealthy and persistent the attacker aims to be through additional actions that we can observe. And of course, different types of attacker activity can be indicative of known threat groups. For example, again, MITRE's attack framework already contains existing patterns of tools and techniques for known APTs. Even more information can be inferred to create the attacker profile. Some of the questions here will be very useful to solve, such as if the attacker is deception aware, or if there are multiple attackers, and if so, are they collaborating or competing? So let's start piecing all of this together. To develop an autonomous cyber deception solution, we need the following. Knowledge of which features to monitor for adversarial activity, check. Some way to categorize the interactions with those features into actions, check. A way to define the current state. We can construct the current state by providing values for each feature and the actions over those features, and over time the weights and values of those features can be improved through autonomous learning. The probability of transitioning to the next state is the meat of the entire learning process, and this is the stage we want deception to disrupt. We'll discuss the state transitions and developing the probability of a state transition in the following slides. So this graphic depicts the high-level state transitions for a deceptive defender's actions, an attacker's actions, and new states created by introducing deception into the network, which provides the attacker with the means to arrive in the new state, which also provides new paths leading towards a false success on a decoy resource. This shows how deception changes the apparent state and actions for the attacker, allowing the defender a strategic advantage. Next, we need to discover how to model the probability that an attacker will transition to a particular state. This probability will rely on attacker goals and expected reward for taking certain actions. Because humans make decisions based on not doing specific actions, but doing actions that can lead to a particular goal, this works very well for the use case where defenders do not know what an attacker's actions specifically are, but based on the results that are observed, we can assume those results are intentional toward their goal. Human behavior is not deterministic, but is driven by a soft optimality, which means we can say that the probability a human is behaving optimally for a given state-action pair can be modeled with a Bernoulli random variable, where R of SA is the reward associated for that state-action pair. However, understanding the reward for a particular state-action pair is not easy, but will be necessary for understanding attacker goals and behaviors. We discuss a different method to seek the reward function that explains this demonstration. Standard reinforcement learning requires a reward function that is able to provide feedback to an agent based on the actions it selects and the states it arrives in so it can learn the best policy. The goal is to learn an optimal policy, but if we don't know that reward, we can't use forward reinforcement learning. The defender does not know the attacker's estimated reward for compromising a target, but the results of the attacker's actions can be observed. And because we need to know the reward to learn the optimal policy, inverse reinforcement learning provides the ability to reverse engineer these rewards through observing the values of actions and states. Once we know these rewards, we can then use forward reinforcement learning to optimize. From Tularosa, which is a static data set, we do not know the reward function, but we can estimate the sample trajectories by parameterizing the states and actions in the participant data. These trajectories can help inform the close approximation of an optimal policy because the study used many experts. The reward function can be depicted as R psi of SA, where psi is the vector that parameterizes the reward. From here, solve the linear reward function with weighted sets of features. This can also be done by using a neural network with parameter vector psi to specify reward function. So through observing these given trajectories, we can learn the parameters of the rewards so that the likelihood of observed trajectories are maximized. From here, we can take our newly learned reward and plug it into a reinforcement learning function and optimize. Currently, cyber defense consists of primarily reactive measures. But with defensive deception, defenders can increase visibility into networks or data, defend systems better by degrading attacker knowledge and performance, and we can learn from the attacker and then optimize and customize deception in a targeted fashion. This brings us closer to predictive cyber defense. In this paper, we demonstrated a sample subset of data that is available to defenders, and the data that can be used to evaluate deception's effectiveness as supported by results from the Tularosa study. These data plus attacker and deceptive actions can be modeled into states that feed an inverse reinforcement learning algorithm to learn the attacker's own reward function based off the assumption they're behaving somewhat optimally towards their goals. Being able to learn the attacker's reward function will enable the creation of autonomous cyber deception solutions, offloading the burden of cyber defense and decision-making from our already overworked defenders. Next steps for this research include parameterizing Tularosa data to define attack states, and evaluating this data for sample trajectories and calculating these reward functions. Follow-on work would include exploring realistic SOC data to test these learning functions on, setting up further experimentation to explore the efficacy of novel cyber deception techniques, and experimentation to use cyber defenders to test this process on defensive decision points to optimize cyber deception over a defender's own rewards. I thank you for your time.